Good afternoon, everyone. My name is Dr. Tanvir Qureshi. I'm a senior scientist in the Canadian Nuclear Laboratories, Ontario, Canada. I'm also a visiting fellow in the University of the West of England in Bristol. And today I'm going to give a presentations on one of my students' work on development and performance evaluations of geopolymer concrete incorporating fly ash, GGBS, and graphene nanoplatelets. The student's name is Christopher Vecchi. And I would like to thank you, the chair, and on the audience of the second international conference on advances in civil infrastructure and construction materials, organized in Military Institute of Science and Technology in Dhaka in Bangladesh, for giving me the opportunity of presenting my work. So the work this is the layout of the presentations. The presentation is arranged in 6 sections, starting with the aims and objectives, literature review, materials and mixing, methods, results and discussion, and then future directions with acknowledgements. Starting with the aims and objectives, the aim of this research is to investigate one-part geopolymer composites, GPC, using a specific grade low calcium waste fly ash and ground granulated blast furnace slag, GGBS, and to develop a pole and cement-free GPC with minimal energy-intensive alkali activators to create a general use composite. The objective is also to explore the impact of the specific grade graphene nanoplatelet GNP on the geopolymer composite systems and achieve optimized GPC mixture with a compressive strength of exceeding 15 megapascal in 28 days. And the objective will be fulfilled by conducting tests such as fresh properties, compressive strength, water absorptions, chloride resistance, efflorescence, and microstructure of the GPC. So starting the literature review, the annual growth rate of ordinarily Portland cement utilization is 4%, and this is expected to raise up about to 200% increment in global demand by 2050. However, this ordinarily Portland cement and the concrete that we produce from it results as significant amount of greenhouse gas emissions, mainly because of the fact that energy intensive decarbonizations of the limestone during the cement production. And that geopolymer binders offer a promising alternative to reduce the carbon footprint of the construction industry. Geopolymer binders use industrial byproducts like fly ash, GGBS with high silica and aluminum content, which reduces the waste and environmental pollution. And utilizing those waste materials in the productions can significantly reduce waste volume, which also offer a secondary environmental benefits. When you look into the benefit side of graphene in geopolymer, again, our literature research suggests that graphene can impact different properties of geopolymer systems, performance of geopolymer systems. That's starting from the composite strength, silicates, and different types of performance efficiency, chemical bondings, alkali activated systems, and then activation energy, and also the cement particles binding properties. Now, when we look into the mechanisms of the productions of the typical graphene reinforced geopolymer concrete systems, what we have actually, we have geopolymer precursors such as fly ash, slag, or metakaolin. We mix that with the activator systems. These are high alkali activators, typically sodium hydroxides or metasilicates. And then we have different types of graphene derivatives that could be graphene, graphene oxide, and reduced graphene oxides. And we have aggregate systems. And then finally, we mix all these ingredients. We also need water in the mixing systems. And then we can produce different types of geopolymer composite systems based on the aggregates presence. That could be ink, paste, mortar, and composites. And the main target of using graphene systems in the composite is to enhance the mechanical properties, increase hydration, reduce porosity, and dense the microstructure, also enhance the and toughens the stress and mechanical properties of the composite system. So the ultimate target here is to replacing ordinary Portland cement-based concrete with GPC to reduce environmental impact, energy consumption, snow materials excavation, and associated cost with it. And the performance of the GPC could be enhanced using advanced nanomaterials, which should be explored. And we have explored the impact of the specific grades of a graphene derivative, which is GNP, produced from Xantech's high purity epigenetic graphite deposit from their Albany mine in Ontario, Canada. And I'm not going to give a detail of how different types of graphene derivatives we have produced in different part of the research and other larger collaborations. However, you can see the main process of the graphene production is so far the chemical exfoliations mechanisms of the graphites, and we can have a single or few layers of graphene. That could be graphene oxide, and reductions of the graphene oxide could be reduced graphene oxide, and we can have mechanical exfoliations using ultracoagulation, ultrasonications. You can have graphene or graphene nanoplatelets as well. So those who are not familiar with graphene is nothing but a single layer of carbon atoms in hexagonal arrangement lattice, which was present in the previous slides. So now you can see a busy slides on materials and mixing, and so a lot of text. I'm going to be walking you through the summary of it. So starting with the geopolymer mix, one of the challenges in geopolymer mix is the 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 substantial variability in the binders, which is fly ash and GGBS. These are waste byproducts. There could be different variations in these waste byproducts and different chemical activators as well. So in this study, we use coarse aggregate, fine aggregates, water, aluminosilicate rich fly ashes, and alkali activators. And then the binders were specifically class F fly ash, which is 80%, and this is low calcium fly ash. It means that less than 5% calcium oxides in the bindings. And then we have GGBS, about 20% of the binder systems. We have two types of alkali activators, starting with sodium metasilicate pentahydrate and sodium metasilicate anhydrous. And the graphene, as I was saying, it is a thermomechanically exfoliated graphene nanoplatelets, about 0.58% of the binders. And in this table shows the properties of the graphene. The characterization shows this. The lattice is about 67.3% of sp2 carbon, and the plane size is about 2 to 3 microns, with the surface areas about 300 meters square per gram. And the number of the layers are about to 10. The curing conditions, so the preparations, one of the things in the preparation is the dispersions of the graphene nanoplatelets in water and then mixing it in the batches. And we follow two curing systems. So curing conditions, one is for batch 1 and 2. This is the mixed design table. And condition 2 is for the GPC 3 and 4. And the first condition, GPC 1 and 2, is just curing after casting in ambient condition. And GPC 3 and 4, we have cured them in the oven for at 65 degrees Celsius for 24 hours after the casting days, actually, and then cured in the ambient conditions. And all the constituents are the same, but again, GPC 1 and 2 batches, and the difference is the sodium metasilicate pentahydrates and anhydrous, so two different types of alkali activators. Looking into the methods, we followed a typical British standards on SLAM test, compressive strength test on 100 millimeter cubes, and water absorption tests. We have little manipulations on the drying process because the samples were dry after dry curing anyway. So we have oven dried them at 105 degrees Celsius for about 72 to 74 hours, and then we have cooled them down for 24 more hours before performing the water absorption tests. We have also performed the chloride penetration resistance test following the typical British standard 12390. And then the specimens in this testing, the specimens were exposed in 23.5% sodium chloride by mass and for 7 days. We have also performed efflorescence in investigation of the samples, visual inspections, also have done some mechanical testing. And then finally, we also perform the microstructure investigation using SCM and EDX. Now, when we started the SLAM test, the simple SLAM test suggests that the GPC4 retains somewhat the true slums, having a range about S3 range, which is about 100 millimeter of the slum, whereas other mixes, GPC 1 to 3, have collapse in S4 category, which is between their collapse are between 150 to 190 millimeter. The major factors of the collapse were associated with the lower liquid to binder ratios, and also we have suggested the increased GGBS content could have increased their workability a bit, and then retain their too much flowability. And of course, this should be quite flowable because you have to know that the geopolymer have high proportion of the fly ash, which was one of the initial target anyway. And fly ash are spherical particles. They allows lots of easy flowing against each particles. However, one point should be noted that addition of graphene nanoplatelet has stabilized the flow properties in GPC4, which you can see in this image. When we look into the setting nature of the composite systems, here you can, the left-hand side image, you can see that composite 1 and 2 have also set, and 3 and 4 has set, but the faster setting has been noted for GPC 4, 3, and 4 due to the high rate of geopolymerization with the related alkali activators and high temperature curing that we have adopted. And they were more drier after 1 day of demolding. And we have also looked into the geopolymers. If we immerse them under the water after just initial day of the casting, like, after we cast the samples and after 24 hours, if we started to cure them in the water like typical Portland cement concrete, and we see that the systems fail because geopolymer need curing the dry conditions. So during, let alone like typical Portland cement concrete, we don't need to cure. Water is not required anymore during the curing process. Looking at the compressive strength results, GPC3 and 4 exhibits much higher compressive strength compared to 1 and 2, as clearly this adaptations of the alkali activator systems from sodium metasilicate pentahydrate to anhydrous and the high temperature curing has significantly impacted it, because GPC2 also have graphene, but didn't show much of the impact on the mechanical properties. So these conditions is quite vital in geopolymer composites. However, additions of the graphene in GPC4 has shown quite remarkable enhancement in strength. So the compressive strength compared to GPC3 and 4, you can see. So the GPC3 doesn't have any graphene and 4 has graphene. So the strength has enhanced about 45% in from GPC3 to GPC4 up to 16 megapascal, and then it was about 55% enhancement in the compressive strength in 34 days compared to the GPC3. And another things could be noted that between the 8 days and 35 days compressive strength, there is not much of the strength gain. So it suggests that the geopolymerizations are typically happen at very early stage of the in the hydration process. So early stage conditioning is quite vital for the strength gain for the composite systems. And you can see the fracture pattern in different mixes. Here is a typical Portland cement concrete, just for a benchmark that how the fracture patterns could be. This is one of the samples in the soup batch, and you can see it's quite crumbling, but GPC 1 and 2, quite brittle nature, as opposed to GPC 3 and 4, quite ductile failure nature, particularly GPC 4 were quite stable while it was cracking under compressive strength. The water absorption results suggest that from chronologically GPC1 mixed to GPC4, the absorption's content has lowered in percentage as 0.54 to 0.31. So GPC3 and 4 showed a reductions in the absorptions by about 37% and 54%, respectively, compared to GPC2, which is a respectable gain in the density of the composite systems as well. And then you can see, of course, this is positive. And it should be noted that GNP didn't show significant advantages in GPT-2 compared to GPC-1 as observed in terms of the strength as well. And appropriate alkali activators and high temperature curing combinations combined with the GNP showed a positive impact on the geopolymer matrix. In terms of the chloride penetration, the surface image shows here after the silver nitrate spray, which shows the dark blue, purple areas indicate that these areas actually has been the geopolymer that we produce as a general grade of the composite systems. It has benchmark compressive strength about 10 megapascal in 7 days or 15 megapascal in 15 days. However, this is a bit less dense, so chloride penetration has happened throughout the samples. However, we could also suggest that the chlorides, the silver nitrate spray effects may not be quite, determining due to the fact that composite systems alkalinity could be low because this is a geopolymer system. So further investigations needed to rule out how much chloride ion penetration has exactly happened in these composite systems. Now going to the efflorescence studies, you can see we compared this. So what we did actually after the water absorption test, we leave these concrete samples in ambient conditions. So we want this water to leach out the ions from the composite systems and to see what efflorescence that happened. And you can see this geopolymer had always this problem about the happenings of the efflorescence. And GPC1 and 2 has more efflorescence opposed of GPC3 and 4. And you can see that we have conducted another set of compressive strength after the initial test. And what we found that GPC 1, 2, 3, the compressive strength decreased up to 10 to 7% actually. However, GPC 4, which has the graphene nanoplatelets, the compressive strength didn't decrease, even slightly enhanced the compressive strength compared to the previous conditions. So it could be noted that GNP have a positive impact or minimum impact after efflorescence in the composite systems. Of course, if we would like to design this geopolymer to protect against efflorescence, we have to be cautious about it. And this is the microstructural investigations suggest that these are the typical geopolymer surfaces, and you can see graphene nanoplatelet has been found, and the composite geopolymers has been more compacted, particularly for GPC 3 and 4, and the geopolymer fly-ash particle where outer surface getting dissolved as well, and several crack patterns can be found, and some places also found that the nanoplatelet might have breaching the crack in the composite systems as well. And we have also performed some semi-quantitative analysis to see the composite systems, and we see that we can. This is again another GNP particles, but we see that most of the contents of the geopolymers have a higher contents of the silicon in the systems. This is silicon-based systems, so it is about 0.4 to 5, as opposed of a comparative between aluminum is 0.1 to 2.8% in comparisons. So each is a typical grade of stable geopolymerizations happened after the geopolymerizations. So in summary, in conclusions, I would like to restrict the optimizations in GPC in mixed design involved using the change of the alkali activator from metasilicate anhydrous to pentahydrate to anhydrous activator systems, and then effective heat curing at 60 degrees Celsius for 24 hours just after 1 day of casting. And this optimizations result desirable compressive strength up to 18 megapascal in 34 days, and 45% reductions in the water absorptions, and up to 10 megapascal strength after 8 days. And microstructure of the system has, the composite has been compacted, and GNP may have reinforced an effect in the matrix. And what GNP has demonstrated is that significant improvement in geopolymer composite and microstructure in terms of exhibiting 54% strength gain in 34 days compared to composite mix without any geopolymer, and 13% lower in water absorption capacity. Also, no impact in the strength after efflorescences. The further research is needed to optimize these graphene reinforced geopolymer composite systems to enhance strength, density, durability against chloride migrations and efflorescence, or any other high performance applications. So when I'm concluding with these slides with the future directions that would like to enhance what we look at the geopolymer composite feature that we come up with, that when we have graphene and geopolymer systems, we would like to say enhance mechanical properties for high-tech sustainable applications. We want to enhance the durability and protect the leaching or absorptions or permeability capacities. We want to have a service life, longer service life as well, and these are sustainable infrastructures and different types of smart properties. I haven't presented any work on the smart properties which are ongoing, such as radiation shielding, heat energy release, monitoring, and sensing. So I'd like to thank you all for listening to my talk, and and I would like to acknowledge my collaborators, of course, Christopher Vecchi on his final year projects in EU Bristol, and the Zantec for collaborating with their graphene materials, and UK Quality Ash Associations for collaborating through their fly ashes. And please feel free to ask any question. You can leave your question to the chair here, chair of the session, and I can get you back. And here is my email and contact as well. You can directly get to me, contact to me as well if you have any questions. In case I'm not available, maybe for the timing, because I'm in Canada at this moment. So please feel free to leave your question to the chair of the session. And thank you so much for your listening.